Hello everyone. Let me give a presentation of our recent public results on robust embedded control. The title of this presentation is Simultaneous Non-Singular Terminal Sliding Mode-Based Robust Embedded Control of Robots. The results have been published in Complexity 2022. The authors are Yixuan Wang, Tairen Sun, and Jiantao Yang. I'm Tairen Sun. In the last several years, we have published several papers on embedded control. The first and the second are about constant impedance control. We improved the embedded control methods by using computer learning and human-robot interaction signals. In the third results, we have constructed the desired variable impedance dynamics and guaranteed its stability by proposing constraints on impedance profiles. There are also some other results include the fifth and the sixth results. It's about impedance learning control used in human-robot interaction in repetitive motions. Let me introduce the background for this presentation. Impedance control is an important active component control approach and has been widely applied in grinding, handling, rehabilitation, and some other applications. However, robot modeling uncertainties they come from include external disturbances and parameter uncertainties. These uncertainties severely affect impedance control stability and robustness. In the last decades, varieties of robust embedded control approaches have been developed based on iterative learning, adaptive control, neural network, and fuzzy logic. But these developed results have some differences. Iterative learning embedded control is mainly applied in repetitive motions. Adaptive control requires linear factorization of robot dynamics. The linear factorization requirement limits the application of the adaptive impedance control. Neural network and fuzzy logic embedded control usually obtains finiteness of impedance errors and cannot get the confidence or impedance errors to zero. In addition, the use of neural network and fuzzy logic usually lead to undesirable computational complexity. There is also a method, sliding mode embedded control. This method can improve control robustness by using sliding mode, but it has a possible chattering problem. In this paper, we improved the impedance control robustness and stability by using simple testing without introducing severe chattering. In this part, we give the robot dynamics in this paper. Consider robot arm with the following dynamics in equation 1, where Q and dot Q denotes the robot angular and the velocity respectively. FQ denotes the inertial matrix. F denotes a knowing robot function. Delta denotes a robot modeling uncertainties. Tau is the control input. Tau E is the interaction force in the joint space. To facilitate the following control design, we suppose the following assumptions. Assumption 1, the desired trajectory QD and its first and second order time derivatives are bounded. Assumption 2, a compact set omega. The uncertainty term delta satisfies that the time derivatives of delta is bounded by a positive constant Dmax. We aim at achieving a desired dynamics in 2, where MD, DD, KD are the impedance profiles and are usually assumed to be positive diagonal matrices. First, let's plot tau E through a low-pass filter in 3. Then the impedance dynamics in 2 can be expressed as in equation 4, where QR equals to QD plus QE denotes the constructed impedance trajectory. Let's define E1 equals to QR decrease Q. E2 equals to QR dot decrease Q dot. Then the impedance error, we define the impedance error EIM equals to the right part of equation to decrease the left part of equation. Then the impedance error can be expressed in the following form. In equation 5. We can see from 5 that the constants of E1 and E2 can guarantee the constants impedance error EIM. Thus, in the subsequent impedance control design, we will design a superposition-based control such that the E1 and E2 converge to 0. The control design is stated as follows. Define the following sliding mode. Equation 6. S equals to gamma E1 alpha E alpha 2 plus E2, where alpha 1 alpha 2 are odd and satisfies the condition. Based on dynamics in 1, the dynamics of S satisfies the dynamics presently in equation 7. Based on this, it's convenient for us to design the following simplicity mode control in it. It's very obvious that this part of the control is the continuous function of time t. Therefore, the control input tau is a continuous time function. under the proposed superracing sliding mode control for the robot with dynamics 1. The impedance error E1, E2, and E2 dot count to 0 finite time. This further guarantees the finite time convergence of EIM, that is the impedance error. The finite time convergence further guarantees the realization of the impedance dynamics into infinite time. To validate the control effectiveness, we make simulations to link robot arm. Where we choose in the simulation, we choose the inactive force as Fe equals to 5 sin 0.2 t, 5 cosine 0.2 t. And the control parameters are gamma equals to 3, alpha 1 equals to 5, alpha 2 equals to 3, Q1 is 8, and Q2 is 10. The simulation results are presented in the figures 2 to figures 4. Under the impedance controller in impedance 4, the error E1 and E2 converge to 0 quickly, which further guarantees the convergence of the impedance error EIM. From this result, we can see that chattering in traditional sliding mode control is not serious. Let's make the conclusions. In this paper, proposes a superracing terminal sliding mode impedance control robot to improve the compliance and robustness of robotic environment induction. The main contribution and innovation of the paper lie in the superracing terminal sliding mode impedance controller. It improves the impedance control robustness without causing chattering. In the near-coming future, we will construct finite-time impedance dynamics. The dynamics can guarantee the convergence of the desired impedance dynamics infinite time if the excitative force is 0. This is very important because the fast convergence of the trajectory checking will improve the human environment in cooperation. We also want to design robust impedance control by using sliding mode observer. That's all. Thank you.